Hey guys, it's been a long time since I posted something about steam engines on my channel, so here it is. I've been, in the meantime, I've been getting a lot of requests for information on how to build this engine. So here it is. I'll try to summarize, give you an overview of the main components and how they're made. So first of all, a bit of background. This is as you can see, a twin cylinder. And it's double acting, which means the steam pushes the piston up, and it also through the valve work, the steam also pushes the pistons back down, and so this way. And also due to the fact that they're dephased, the two pistons are dephased by 90 degrees or quarter turn, you get a constant torque on the crankshaft, so which makes it also self-starting, so you don't need to give it a swing like you would for a single cylinder engine. So I guess let's go through it in a little more details. So we'll assume this is number one and this is number two cylinder. And I just said that they're dephased by 90 degrees or a quarter turn. So what that means is that when number one is at top dead center, which is the piston is fully extended, the other one is at mid travel, so about halfway through, and the its lobe, I guess I'm not sure what you call these, but the throw, I think, is at the top mark. So it's always following a quarter turn behind number one. So this one is at the top here, quarter turn later, the other one is following. So that's principle number one for a smooth running twin cylinder engine. The other thing that you need to know, I guess, when you design your engine, is that the valve. So we'll take number one cylinder, for instance. The valve is also following the stroke the stroke of the piston by a quarter turn. So if I put the number one at top dead center, the valve travel is right at the mid range spot. So always a quarter turn behind. So these lobes here are designed so that it's 90 degrees behind. So number two is quarter turn behind number one, and the valve for number one is quarter turn behind the stroke for number one, and same story for number two. The valve quarter follows the stroke by 90 degrees behind. All right, so if we do that in slow motion, number one is at top dead center. Number two is at top dead center now. The number one is at the bottom stroke. And so on. All right. So as far as the construction itself, I guess the most challenging part is the crankshaft, and I'll probably have to have a separate video on how to make this, because I'm going to be making a new one sometime soon. I just have to get around to it, and it's not an easy task, but it's certainly doable with basic your basic tools. Really, I didn't need a lathe for this. You just need to know how to solder and be pretty accurate in your work. So here it is. As far as materials, these are built from simple brass tubes from hobby shops, and actually the material for the next one is right here. So the cylinders is from this tube here, so that's 19/32 of an inch diameter. Now you take whatever you can get your hands on, right? But there's a couple of things. You'll need to find a piston of some sort that can fit in there, and we'll go through that. Here's a 3/16 inch brass rod, which is used mostly, well, for the piston rods here, and also the crankshaft, the main part of it. You also need some 1/8 of an inch rod for the different other parts, like these rods here, and also some parts in the crankshaft and so on. Some 7/32 brass tube. This is used for the valve body here. So the valve itself is a 3/16 inch brass rod that we're going to have a closer look later, which fits exactly into a 7/32 of an inch tube. So that's quite convenient. You need some plate like these to build the crankshaft, the lobes, and so on. And you'll also need this sort of tube, which is 5/32 of an inch, for all the bearings, bushings, bearing, whichever. So right here, and there, and so on. So that's it in essence. We'll take it apart, partially at least. And we'll take one of the valves out, and both number 1 and number 2 valves are identical. They can be interchanged. So here it is. That's basically what you have to achieve. And I don't have a metal lathe, so I do this using my drill press here. And I installed one here just to demonstrate. So what I do is I spin the rod against either a file or a saw, or even a grinder. You can use a Dremel with a grinder tool on top. So oh, I guess it's not connected, but you spin this, and then you grind these part. You need to leave these two seats, which are the actual valve. Now the distance, of course, has to match the ports. So the steam ports are there's one at the bottom, there's one at the top, and so it's basically a hole between the valve body here and there, through the cylinder wall, and to feed the steam in. What else is there to say? So that is the valve, and I guess you could see that it would work. It simply moves this way and that way, and that's about how much travel there is, really. I'll take one of the pistons out, because I left. If I can get this pin out. Thank you very much. All right. I left one bottom here, one cap off, so that we could take the piston out. So here it is. How do I make these? Good question. These are made from brass bushings that you can buy at your local bearing store, I guess. Here in Canada is General Bearing. And so remember, the cylinders are 19/32 of an inch, and a bushing by the size of 9/16 will fit pretty much in. It's going to be tight, and you're going to have to work it. You're going to have to file it down or machine it so that it fits right in and it slides. Now, the problem I had is that you need a bushing 9/16 of an inch outside diameter, and the front, the center, the rod is 3/16. So that would be a 3/16 by 9/16 bushing, which does not exist, at least in the shop that I went to. So the other solution is that you get two different bushing. So that's the larger bushing. That's the 19/16 of an inch, and you get another one which is 3/16 by 3/8, which fits right on the rod, right like that, and it also fits right in there. So what you do is you assemble these together. Anyways, I have only one hand to work with here, and it's and these are a little larger. You can see here they're 1/2 inch long, and so that's how you build your piston. And I made a groove on the side. Apparently this helps lubricating. So same story. You just put it on your drill press, you spin it against a metal saw and or a file or something, and you make that groove. So that's pretty simple. This part, actually, what you see now is actually this assembly of two bushings is exactly what you're finding, what you get for the top, for the top seals. Because you need a seal there because it's double acting, so there's steam pressure that comes at the top, and you need the top to be tight. So that's how, same bushings really, that's how you do it. The bottom, once the piston is back inside, you need to make some sort of a cap, and you could probably weld a plate here, but it's kind of nice to be able to remove the piston. So that's the same story. It's really these two bushings, and with a brass rod in the center hole. That's just assembled together and soldered, and then it fits right in. So yeah, something like that. But anyways, all right. So that's pretty much it. There's several choices that you need to make along the way. For instance, what's going to be your piston travel, and what's going to be your valve travel, and so on. And you need to really put the pen to paper and figure out for yourself how that works, and the dimensions and all. But I can perhaps try to help there. But so I decided to go for a 10 millimeter throw, which when you multiply by 2, okay, so I'm having trouble illustrating what I'm saying here. But anyways, I'll rephrase this. I decided to go for a 20 millimeter piston stroke total. So the piston goes from here, about here, I guess, once it clears the bottom cap, and it travels all the way to there, and that's 20 millimeter. Wherever you measure it moves by 20 millimeters. And of course, so that's pretty arbitrary. It could have been 18 millimeter, it could have been 25 millimeters. I guess the more travel you get, the more steam consumption and so on, just a bigger displacement. So if it travels by 20 here, the throw needs to be 10 millimeter because a full turn will bring it all the way down by 10 and all the way up by another 10. So that's a total travel of 20 millimeters. So that's pretty arbitrary. And then the valve, well, there's a couple of principles that you need to understand, but when it's at neutral position, these two faces, I guess I will call it that, are exactly blocking both holes, both ports into the cylinder. And then you need to, this much travel, I guess, something like that, to clear, to open up the port to leave the steam out. And then it needs to come back down and clear the hole again to let the steam in. And same idea at the top. So for me, a throw of 6 millimeters at the crank, which means a travel of 12 millimeters, works. It's a function of how big these surfaces are, how long. So you need to clear them. So I could have gone, I guess I could have gone, if I went 10 millimeters for the main throw here, I could have gone the same 10 millimeters for the valves, except if you do that, then the valve just travels way too far for no particularly good reason. So it would travel typically about this far down, which means you need to have a longer valve body, and then it'll move higher up as well. So it's just not very elegant, but it would work just the same. Perhaps it might produce a little bit more wear onto the valve. I don't know. But anyways, it's for me, I figured 6 millimeters each way works. So I didn't explain really the details of how this valve works. I guess you're going to need to figure it out yourselves. But I'll just say that notice that this narrow part there is always under steam pressure. So the steam comes in here, and that's an open hole into the valve body. So this part here is always pressurized. And then depending where on the position of these surfaces, these two faces, once it clears the bottom port, then this pressure comes and feed the bottom part of the cylinder and pushes the piston upward. And then same idea, the valve goes back up. At that point, this face clears the port, which opens it up to let the steam out to the air, I guess, into the manifold here. And then this face clears the port, and this pressurized part here, this pressurized area, comes and well, the steam will then enter the top port and cylinder chamber and push the piston down. So I'll try to reassemble this and show you a little better. So what I did is I reassembled the valve, and I also reinstalled the piston here so that I can swing or turn the crankshaft freely. And I just wanted to show here how things move, how the valve moves relative to the piston. So that would be the valve in this position would be the neutral. Neutral. I'm just grabbing a pen here just to illustrate something. And I'll draw a mark here and another mark there. So what happens when I say neutral, it means really halfway between the top and the bottom, following this lobe of the crankshaft here. So right at the center, the valve is there, and it pretty much faces these two ports exactly right in the center. So that's when the lobe is at the top here, or in neutral position. At that point, the crank keeps turning, and the top port just opened up because we went this way, and you see the piston is starting to come down, and at that point the steam will push the piston down, and the bottom here, the bottom port is fully open into the manifold and to the air. So whatever steam is left in the cylinder is pushed out, and then until the piston reaches the bottom, and then the valve closes at the same time. You see that the top is closed, so we're done pushing the piston down. We're in neutral here because and then if we keep going, the piston moves up a little bit. At the same time, the bottom port opens up to let the steam in and push the piston forward. At the same time, the top port is now open because the face here has just moved down, which allows the steam, which is on the top part of the piston and in the top part of the cylinder, to be pushed out through the port and inside this I guess it's really hard to see here, but inside the valve body, and there's a hole, and of course this shoulder here on the valve prevents the steam from exiting through the valve body. So it has no other place to go other than this into the exhaust manifold. So, and then starts over again. So the number 2 cylinder does exactly the same thing. So I don't think I need to go through the details of that. It's just that so we remember that number 2 follows number 1 by a quarter turn, and the valve follows its piston by a quarter turn as well. So when this is at the top, this is on the side here at the bottom stroke, and then this is at top dead center, and this is right at the neutral position. So quarter turn behind. All right, well, I hope this clarifies things a little bit. I could talk a lot more about other details. The flywheel is cast out of lead. I have a video on that. It's not on my channel yet, but I will eventually put it on. That was an interesting experience or experiment, but yeah. And so, yeah. What else is there? The boiler is a can of soup, 680 milliliter can of soup, and so I made this is a I guess, yeah, that's a safety release valve that I sort of made. That doesn't really work all that well, but anyways, it works. And this is just a regular bicycle tube valve I guess I fill it up through there. And you can also measure the pressure if you want to while it's running. So anyways, let me know if you have any more questions and I'll try to answer them. Thanks for watching. Bye-bye.